Hello everyone, welcome. In this video we will talk about the procedure for solving linear differential equations using the method of integrating factor. The first step is identifying that we are indeed dealing with a linear differential equation. We can verify this by inspecting our equation and noting that we do not have any y's present anywhere in our equation that have an exponent other than 1. If we were to have a y squared instead of y, this would not be considered as a linear differential equation, rather it would be considered as a nonlinear differential equation. Similarly, if dy squared dx were to be present instead of dy dx, this would also make the differential equation nonlinear. Also, if there was a y times dy dx present, this would also make the equation nonlinear, since it's tantamount to having a y squared dependency in the equation. A square root on the y would also disqualify the equation from being linear. Only single orders of y must be present in the equation for linearity to be maintained. Now that we know that our equation is linear, we can consider the following general form of a first-order linear differential equation. Here, a sub 1 of x and a sub 0 of x are coefficients that may depend on x or may be constants. B of x, again, may only be a function of x or may be a constant. What we want to do to start the solution procedure for this type of equation is to put the equation in what is called standard form. The procedure for putting an equation of this type into standard form is to simply divide by the coefficient in front of the derivative. The resulting quotients in front of the y and on the right-hand side of the equation we redefine as p of x and q of x as such. This puts the linear differential equation into standard form. What we want to do next is generate what is called an integrating factor that will help us determine the solution to the differential equation. For this type of problem, the integrating factor mu is always equal to e raised to the integral p of x dx, where p of x is the coefficient in front of the y when our linear differential equation is in standard form. After evaluating the integrating factor mu, we then simply multiply the entire equation by mu. When we do this, something very convenient ends up happening. The entire left-hand side of the equation becomes the same thing as the derivative of mu times y. This happens every time provided that mu was evaluated correctly. What we are essentially doing here is applying the product rule of derivatives in reverse. This is convenient because this now transformed differential equation is separable and can be solved using the usual procedure for separation of variables. Once we separate and integrate both sides, we can express the solution y as the following, where k is the redefined integration constant from integrating the left-hand side. Let us consider the following example. We are asked to solve the initial value problem x times dy dx minus y minus x squared times e to the x is equal to 0. We are given an initial condition y at x equals 1 is equal to e minus 1, which we can use later in the problem to determine the integration constant. The equation is first order since the highest derivative on y is 1, and it's linear since all y's present in the equation are raised to the first power. This means we can use the method of integrating factor to determine the solution to the equation. However, we first need to put the equation into standard form. We can accomplish this by moving the third term over to the right-hand side, and then dividing the x coefficient in front of the derivative, and then making simplifications. After doing this, we end up with the following differential equation in standard form. We can begin the process of generating the integrating factor by taking note of p of x and then evaluating the integrating factor mu using p of x. After plugging p of x into mu, the evaluation of the integral in the exponential results in negative natural log of x. Here we take the integration constant to be 0, since it will not affect the procedure. As we'll see, any integration constant would have cancelled on both sides of the equation. We can apply some rules of exponents and cancel the natural logarithm with the base e, which results in mu simply being equal to 1 over x. We can multiply the entire equation by mu, which is simply 1 over x, and make some simplifications. After doing so, we end up with the following. While it may not be obvious, the left-hand side is actually much easier to deal with since it is simply the derivative of the product mu times y. You can double-check this by differentiating mu times y using product rule, and you'll see that it's exactly the same as the left-hand side. This happens every time as long as you followed the procedure and generated mu correctly. So long as you're confident in your procedure, you don't always have to check by taking the derivative. This form of the equation is especially convenient because it is a separable equation, which means in order to solve for this, we can move the x's and dx on one side, and instead of y, we have the product 1 over x times y as our dependent function. We can allow this to remain on the left-hand side, and then integrate both sides. The integral of d1 over xy is simply just 1 over x times y. We will hold off on the integration constant for now, and allow it to absorb into the integration constant on the right-hand side. On the right-hand side, the integral of e to the x dx is simply just e to the x plus c, where c is the difference between both integration constants on the right and left side of the equation. We can then solve for y using some basic algebra, and we end up with the following. Let's not forget about the initial condition, y at x equals 1 is equal to e minus 1. We can use this to solve for the integration constant c by plugging in 1 for x and e minus 1 for y. After doing this, we can solve for c algebraically, which results in c being negative 1. We can plug this into our original general solution, and after making some simplifications, we obtain the following solution to the linear differential equation.